So a couple of weeks ago, I asked you in your survey if you had found any themes to the Mathematician Spotlight or any patterns. And some of you said things that I would say are correct, and I'll tell you what the theme is at the end. But someone said, all the Mathematician Spotlight people are professors. I was like, oh, yeah, that's true. I didn't think of that. So I'm going to branch out and tell you about some graduate students. So this is Yajnaseni Dutta. She's a graduate student at Northwestern. And she studies birational geometry and Hodge theory. So I thought I'd tell you a bit about what birational geometry is. So it studies when two curves are related by a simple function. So for instance, things that we've done, if you have the unit circle and you want to turn it into like an ellipse, you could take every point on it and you could take x and send it to like 3x, and you could take y and send it to like 1.5y, something like that. And that would take this and go whoosh, by a factor of 3 and whoosh, by a factor of 1.5, something like that. Another thing you could do is you could take the unit circle and turn it into the real line. So for instance, here's a unit circle, and here's the real line. It was supposed to go through the middle. It didn't quite happen. Oh well. And you might wonder if these two things are related by a simple function. And so one way to do it, there are a couple ways, but one way to do it that's kind of cool is if you take the point t comma 0 here on the real line, you draw the line between that point and the north pole of the circle, and you say this is the associated point, x comma y. So you associate to each point on the real line, or on the x-axis, I mean, a point on the circle. And you can say what to do. X of t is something like 2t over 1 plus t squared. And y of t is something else, like 1 minus t squared over 1 plus t squared. And this is called a rational function because it's like a ratio of polynomials. So that's what the idea of birational means. It goes back and forth with a rational function. You could also say t comma 0 goes to cos t sine t or something like that, but that wouldn't be as simple of a function as these polynomials. So it studies when two curves are related. That's the idea. Yeah. So you too could go to graduate school and study cool functions. That would be nice. All right. I think I turned some of the lights off instead of turning the lights on. We'll try that again. Two of them are labeled rear. So confusing. Okay. So perhaps you recall that the theme for the rest of the semester is we're integrating some kind of functions over some kind of things. So for the rest of the semester, we are integrating scalar and vector valued functions over curves and surfaces. So last time, we talked about scalar line integrals. That's integrating scalar functions over curves. So this is last time. And today, we'll talk about integrating vector valued functions over curves. So this is today. That's the idea. You'll have a vector field and a directed curve and integrate the vector field over the curve. That's the idea. So before we do that, though, let's just do an example of scalar valued line integrals so that you remember what's going on. So, for example, this is a scalar line integral. So integrate f of x, y, z equals, what shall we do? Perhaps a good function might be z squared minus 12y plus z over the curve defined by x of t, that's a vector, is t cubed 3t squared comma 6t from where t goes from -1 to 2. Okay, so you can think of this as being some curve in space. That's what it is. At t equals -1, where it starts, the point would be, so at, who knows what it does? At t equals -1, it is -1, comma 3, comma -6. That's where it is. And then it goes along its merry way for a while. At t equals 0, it's at the origin, 0, 0, 0. Because if you plug in t equals 0, you get 0, 0, 0. And when t equals 2, it's something else. Where is it? It's at 8, 12, 12. Okay, so there's the function. There's the curve. It's going along. And then the function associated, and this is in 3 space. I've drawn it in 2 space because I only have a 2-dimensional chalkboard, but it's in 3 space. The function associates to each point some function value. So maybe it's, who knows what it is exactly. I'm not sure where, but in some places maybe it's negative, and in some places it's positive, and it adds up the function value on all those points. So let's do it. So, so we'll compute the line integral over c of f ds, which is the integral from t equals -1 to t equals 2 of f of x of t times the magnitude of x prime of t dt. So that's what we're going to compute. Let's get the parts. So the first thing we need to do is find parametric equations for C, for our curve. Our curve, which I have schematically drawn here. Oh, but we have them. Already done. Okay, great. Okay, the second thing is we need the speed vector magnitude of x prime of t, because we're going to plug it in here. So let's do that. So we have x of t is t cubed, 3t squared, 6t. So let's compute x prime of t. Derivative term by term is 3t squared, 6t, 6. So that was sort of a clever little function. Each component is the derivative of the previous one. Okay, and now we want, so this, by the way, this is the position. X of t is the position. X prime of t is the velocity. And when we find the magnitude of the velocity, it will give us the speed. So let's do that. The magnitude of x prime of t is the square root of, let's see, 3t squared. Squared is 9t to the 4th. 6t, that whole quantity squared, is 36t squared. And 6, that thing squared, is 36. And you might think, oh, I know, I can factor this. You can factor out a 9. It turns out that the whole thing factors to 3t squared plus 6, square root squared. So it turns out that the whole thing factors. Kind of nice. And so this square root of quantity squared is just 3t squared plus 6. And you might be worried, maybe it should be absolute value, but notice that 3t squared is always positive, 6 is always positive, so the quantity is always positive. Don't have to put an absolute value. 3t squared is always non-negative. Okay. Okay, so that's the first things. And now, a last thing that we need is we need f of x of t so that we can put it in. So you could do this. You could just write out this integral and then compute everything on the fly, but I thought it would be more systematic to compute them all in advance. So that's what we're doing, because I'm in charge. Ha! So let's see, f of x of t. We know that f of x, y, z is z squared minus 12y plus z. Is that what it is? Yes. So, and we know that x of t is t cubed 3t squared 6t. So what we want is f of t cubed 3t squared 6t. That's what happens when you plug this in. All right, f of x of t is what happens when you substitute in x of t for x, y, and z. So let's see. Z squared is 6t squared. 12 times y. Y is 3t squared. And plus z is 6t. Okay, so the idea of this is that we knew what the function value was at any point x, y, or z. It was this thing, z squared minus 12y plus z. But now, in order to compute this integral, we want to know what the function value is at each time. Hey, it's 1 o'clock. What is our function value? Hey, it's 1:01. What is our function value? So this tells us our function value is a function of time. Okay, let's compute this out. 6t quantity squared is 36t squared. 12 times 3t squared is 36 negative 36t squared plus 6t. So these two parts cancel out, and the function value is just 6 times t. So the function value is 6 times whatever time it is. Pretty nice. So now, actually, we can go back to our picture. I didn't know whether the function was going to be positive or negative at each point, but now we know. At the beginning, when t is negative, it's negative, so it's 6 times t. So at the beginning, the function value is negative 6, and then the function value gets negative, less and less negative. It's 0 at 0, and then it's positive afterwards. And it gets more and more positive as t gets higher. It's harder to draw pluses, but you get the idea. Lots of pluses at the end, because the function value is like positive 12 at t equals 2. So now we can guess the function value is negative at the beginning and positive at the end, but it looks like it's probably more positive than negative. It's possible that the curve just like winds around a lot at the beginning and it's very long at the beginning, but probably we expect a positive answer. So expect an answer greater than 0. Okay, let's see what we get. Okay, I think we have all the parts now. So the integral from t equals 1 to t equals, negative 1 to t equals 2 of f of x of t. F of x of t, we figured out that was 6t. So this is our f of x of t part. Times the speed. Oops, this was supposed to be yellow. Let's make it yellow. There. That's our f of x of t. Times the speed vector, we computed that. That's 3t squared plus 6 dt. And now we just compute this integral. So there are some ways to do this. It's just a polynomial, so you could just multiply it out and take the antiderivative term by term. But another way to do it would be to recognize that this 6t is the derivative of the inside of this function. So if you could just make this a function where you had to take the derivative of the inside, you'd be all set. This is something that came up on the exam as well when we had to integrate cos t times sine t. So a clever thing to do would be to say this is 3t squared plus 6 squared, and then multiply by 1/2. That's the antiderivative. Because if you check it, take the derivative of this thing, it's 2 times 1/2, cancels out the constants, times 3t squared plus 6 times the derivative of the inside, which is 6t. So it looks like it is the antiderivative for what we want. So we'll evaluate this from t equals negative 1 up to t equals 2 and get 1/2 times, now we have to plug in. So when t equals 2, 3 times 4 is 12, 12 plus 6 is 18. So this is 18 squared minus, plug in t equals negative 1. Negative 1 squared is 1, 3 times 1 is 3, 3 plus 6 is 9. Okay, 9 squared. And so if you compute this out, it comes out to 243 and then divided by 2. And it's positive, which is what we thought it would be. So that's good. Yeah. Questions or ideas? All right. So that's the idea of scalar line integrals. And now we'll talk about vector line integrals. So let's do it. So vector line integrals. Vector line integrals are also integrals over curves, although they are called line integrals. The lines can be curved, which is troubling, but fine. Okay, so the idea is that you have a vector field. So I'm going to draw some nice vector field. So here's a vector field. You can think of this as being like the way that the wind is blowing at any point, or the way that the water is flowing at any point. So here's a vector field. There we go. Okay, there's our vector field F. And I've drawn it actually so that all the vectors are the same length, but the vectors don't have to be all the same length. They can be different lengths. Okay, and now you imagine you have a curve C going through this. So if you're thinking of this as being like water, you can think of C as being your canoeing path. So, for instance, you're going along like this. There. Okay, there's your canoeing path. And when you take a canoeing path, it's always in some direction. So this is a directed curve. So there we go. There's our path. So a vector line integral is given a vector field F and a directed curve C. So a curve with an orientation, a curve that you know where it's going. The vector line integral of F over C, well, it measures how much the vector field points in the same direction of the curve. So you can think about that as like how much the current helps you or hurts you along your way. So it measures how much F points in the same direction as C. So how much it points in the same direction as C. And in particular, we call this the line integral over C of F dot ds, where this is a small s, meaning the infinitesimal arc length in a direction. So s has a vector because it's infinitesimal arc length in the direction of the curve. And we compute this as the integral over C as f dot t ds, where t is the unit tangent vector in the direction of C. So the reason we do a dot product is because a dot product is like a measure of how much two vectors point in the same direction. So if you have two vectors, let's just for now say that they're unit vectors. The unit is the length of my fingers. If you have two vectors and they point in generally the same direction, their dot product comes out positive. The angle between them is between 0 and 90 degrees, so the cosine is positive. The dot product says, okay, if your two vectors are within 90 degrees of each other, the dot product is positive, they point in the same direction. I think I just said the same thing like 4 times. I'll try not to do that. Okay, so then if you have your two vectors point in opposite direction, in perpendicular directions, then their dot product is 0. So if one of them, you would say they're not pointing in different direction, same direction, or different directions, they're pointing in perpendicular directions. And if they're pointing in opposite directions, or close to opposite directions, if the angle between them is between 90 and 180, then their dot product comes out negative. So that's a nice way of doing this, because when the vectors are pointing in the same direction, the number comes out positive. When they're pointing in different directions, it comes out negative. So let's consider this for a couple of points along this curve. So how about at this point? So at this point, the unit tangent vector, who knows how long a unit vector is? Maybe it's this. So here's the unit tangent vector. And here is the vector field vector. And the angle between them, let's call it theta 1. So theta 1 is less than pi over 2. So f dot t is, theta 1 is greater than pi over 2. So f dot t is negative. And this should be pretty clear that the vector field is pointing in a different direction than the curve. If you were canoeing here, you'd be going against the current. It would be so hard. So that should contribute a negative amount to our integral. How about here? So here, our vector field vector and our, that's F, and our unit tangent vector are perpendicular. So our theta 2 is pi over 2. So F dot t is equal to 0. So this point contributes 0 to our integral because the current is just going against you. It's not helping you, it's not hurting you. In the canoe example, it's probably hurting you because it's actually pushing you to the side. But in terms of getting to where you're going, it's not helping you or hurting you. And then how about over here? So right here, the vector field F is going this way, and the unit tangent vector is going this way. And so the angle between them, theta 3 is less than pi over 2, and F dot t is positive. They point in generally the same direction. So that's contributing a positive amount to the curve. Yeah. All right. And it depends the size of the vector. So if this, let's see, which one is smaller? I don't know. Maybe this one is bigger. Maybe this F vector is very big. So if the unit tangent vector is always unit length, but if F is very big, the dot product comes out bigger. Here, maybe our vector field vector is quite small. The unit tangent vector is the same size, but the vector field vector is smaller, so the contribution would be smaller. So this negative number that was from F dot t over here would be smaller than the positive number from F dot t over here. Yeah?
It's kind of off topic, but what's the equation for dot product again? Goes on there times.
Yeah, so if you have any vector u dot v, it's equal to the size of u times the size of v times cosine of the angle between them. So in our situation, we have F dot t. So that's equal to the magnitude of the vector field vector times the magnitude of t times the cosine of the angle between them. And since our t is always a unit tangent vector, this is just the magnitude of the vector field vector times the cosine of the angle between them. So when the angle between them is between 0 and 90, cosine is positive. So this comes out positive. When theta is 90 degrees, this comes out to 0. And when theta is bigger than 90 degrees, between 90 degrees and 180 degrees, this comes out negative. Yeah. All right. And one last thing before you do an example yourself. So suppose you're integrating over some curve, f dot t ds. Like you start on your canoeing path and you canoe to the end. And then you decide that actually you're going to go the other way. You're going to go back along f dot t ds. How would you say these things are related? Yeah, they're the opposite. Because if the flow is hurting you on the way out, it'll help you on the way back exactly the same amount. So these are equal and opposite. When you change the sign of c, you change the sign of the whole integral. Yeah. Okay, so on your sheet, on the back, you have an example of a vector field with 5 curves going through it. So could you please decide whether the integral over each curve is positive, negative, or 0, and check with your neighbor? Great, go. Okay, so let's talk about them. So the vector line integral over C1, this sort of unit circle counterclockwise thing, what would you say? Is it positive, negative, or 0? Positive, yeah, why? Yeah, it's always with the flow. It's always, here it's going, the vector field is just pushing it around, so this should be positive. Oh man, you can see the answers. That's not good. Too late, maybe. Okay, positive, yeah, great. How about C2? Positive, negative, or 0? 0, yeah, why?
Because they're equal opposite. Like you go with the flow, then you go against the flow.
Yeah, you go with the flow, then you go against the flow, and they're equal and opposite. Yeah, any little calculation you did over here would be exactly the opposite calculation over here. So what did you say? It was equal to 0. Yeah. How about C3, this one over here? Positive, negative, or 0? Negative, yeah. Why? Yeah. Did you? I don't know. Catherine, you had an idea? Okay, someone else? Yeah.
Because initially when it goes against the flow, it has a stronger, what did it say? It's stronger when it goes against the flow.
Yeah, it goes against, initially it goes against the flow quite strongly. And then?
And then it gets weaker when it goes with the flow, so the negative exceeds the positive.
Yeah, nice. Then it gets weaker when it goes with the flow, so the negative exceeds the positive. I don't know if this happens to you, but I feel like this happens to me when I'm running. I'm going out and I'm like, oh man, this headwind, it's so bad. It's slowing me down so much. And I'm like, well, at least when I turn around and go home, it'll be helpful. And then you turn around and go home and you're like, excuse me, is there any wind at all? And it doesn't help you. So the part that is hurting you exceeds the part that's helping you, so this should be negative. Yeah. It's because the wind is going with you and you're going the same speed, so you can't feel the wind when it's coming with you, but it's still helping you. Okay, how about C4, this one right here? Positive, negative, or zero? Negative, yeah. Yeah, why? It's going against the flow all the time, yeah? Okay, so it's like maybe you have some sort of nuclear power plant on both sides of your river just pushing water into your river at this weird angle, and you're trying to go upstream. Not working. So this should be negative. Great. How about for C5? Positive, negative, or zero? Zero, yeah, why? Someone? Yeah.
Flow is just perpendicular.
Your flow is just perpendicular all the time, so the contribution at every point is zero. So it comes out. Is zero all the time, so zero. Yeah, nice. Okay. Great. Yeah, this is, maybe in this one, our canoeing metaphor breaks down a little bit, because if you were canoeing and you had this cross current the whole time, you'd feel like it was hurting you. But if all you're trying to do is just get north or whatever, then it's not hurting you from getting north. Okay. Okay, so so this is what you should be thinking of when you are computing vector line integrals. You should be thinking, I'm figuring out how much the vector field is pushing me with the curve and how much is pushing against the curve. That's it. Okay, so let's compute some with some equations. So we'll do two different methods for this. Oh, that's good enough for now. Okay, so method one is sort of being clever and using the function and the curve together. So for example, let's compute the vector line integral of the function, let's see, x squared plus something. Let's see, what is it exactly? X squared plus y, comma negative x plus 1 times y over the curve C, which is C1 and then C2. So however you want to call C1 and then C2. So here's what they are. So curve C1 is the horizontal curve that goes from 0, 0 over to 2, 0. There's C1. And then C2 is the vertical curve, which is actually a line segment that goes from 2, 0 up to 2, 2. Okay, so C consists of, please follow C1 and then follow C2. That's the idea. So let's see if we can do this. So let's first talk about C1. So on C1, we'll see if we can simplify anything at all. So the vector field on C1, well, C1 is just along the x-axis, so y equals 0 there. So on C1, y equals 0. So our vector field, which is x squared plus y, negative x plus 1 times y, is just x squared comma 0. All right, so plug in y equals 0. It's just x squared comma 0. Now we're going to want to compute f dot t ds at every point. So let's get a unit tangent vector in the direction of C1. Well, C1 just goes to the right, like in the positive x direction. And on C1, the unit tangent vector is always just 1, 0, just going to the right. So our unit tangent vector always looks like this, t, going to the right. And our vector field is x squared comma 0. So at 0, that would be 0, 0. And as x gets bigger, that gets bigger. So it looks something like this locally right around here. It always points to the right, but gets bigger and bigger. So on C1, f dot t is x squared comma 0 dot 1 comma 0, which is x squared times 1 is x squared, 0 plus 0 times 0 is 0. Check it out. Also, ds is our little arc length amount. It's like dt or dx or dy. But look, along the x-axis, it's just dx, because we're just going along the x-axis, or in the x direction. So it's just dx. So the integral over c1 of f dot t ds is the integral of f dot t, which is x squared, times ds, which is just dx, from x equals 0 to x equals 2. And that you can do. That's just x cubed over 3 from 0 to 2, which is 8 over 3. So it tells you that the vector field helps you. It's pointing in the same direction as the curve, which is pretty clear from this picture. The little red vectors, vector field, are all pointing to the right, just same direction as C1. And it helps you to the amount of 8/3, whatever that means. Okay, cool. We've done C1. How about C2? So on C2, the vector field, which is x squared plus y, negative x plus 1 times y. So on C2, this is just the line x equals 2. So x equals 2. So we can just plug in 2 for x. So x squared plus y is 2 squared, which is 4, plus y. And x plus 1 is 3, so this is negative 3y. So that's just what f is. So let's draw that in, whatever that looks like. So when y equals 0, this is 4 comma 0. So it's just this going horizontally. And when y is 2, it's like 6 comma negative 6, which is like this. And in between, it kind of interpolates somehow. So the vector field looks something like that along the curve. So we can guess that the vector line integral along this curve is going to come out negative. Because at the bottom, the vector field is perpendicular to the curve, and at the top, it's kind of going in the wrong direction. It's going against. Okay, so there's f. And also t, our unit tangent vector, well, we're going vertically. So it's just 0, 1. And ds, we're going vertically, so ds is just dy. So ds is dy. So the line integral over C2 of f dot t ds is the integral of f dot t. Let's see, maybe I should compute this here. So f dot t is 4 plus y negative 3y dot 0, 1, which is 0 minus 3y, so negative 3y. So this is negative 3y times ds, which is dy, from y equals 0 to y equals 2. So that's negative 3y squared over 2 from 0 to 2, which comes out to negative 6. Okay? So we expected that it would be negative because it looks like the vector field is always working against us, and it did come out negative, negative 6. Okay, so the vector line integral over C of f dot t ds is the vector line integral over C1 of f dot t ds plus the vector line integral over C2 of f dot t ds. We figured out that the first one was 8/3, and the second one was negative 6, and that comes out to something, negative 10/3. So it tells you that the vector field is working with you along the first curve and against you on the second curve, and it worked against you more than you worked with you, so net, it's against you. Yeah?
What kinds of units will this answer have?
What kinds of units will the answer have? Ooh. Right. Let's see. I think it's work. So if the vector field is, it's the total amount of work that the vector field does on the curve. So I think the units of work are, what are they? What? Newton times meters?
Yeah.
So kilogram meters squared per second squared, something like that? Okay. Yeah.
So the reason that this was negative is because the vector field around C2 is just bigger vectors, and they happen to be against, like the values of those vectors are larger, right? And that's why it comes out to a net negative value.
Yeah, that's right. So we got a positive value for the vector line integral over C1 and a negative vector value for the vector line integral over C2. But these vectors, these start out very small because it's x squared comma 0. So for this whole first part, the magnitudes of the vectors are less than 1. So they're actually quite small. My picture maybe is not to scale. And then, I see, yeah. And then they get to length 4 over here. But at the top, this vector is what, like -6, -6, or 6, -6. So the vectors along this green curve are quite big. So the small contribution here in the positive is outweighed by the big contribution here negative. So my vectors are roughly, I mean, not to scale exactly, but yeah, some big vectors going against you here, and little vectors going with you here. Yeah. All right. So you might be thinking, well, gosh, that was so convenient that worked out for you there. But this is not always going to happen. My curves, for example, might not always be horizontal or vertical. So what should I do then? And it turns out we can figure out a formula for what happens in general. Okay. So the vector line integral. So the vector line integral over C of f dot t ds. Well, we want to turn this into an integral that we can compute. So like we parameterize our curve with time, and we integrate it with respect to time. So this is the integral from t equals something, maybe a, up to t equals b. So let's C be defined by x of t from where t goes from a to b, of f of x of t times, the tangent vector, the unit tangent vector. That's the way you're going, so that's the velocity vector. So this is x prime of t, but it has to be a unit tangent vector. So you have to divide by how fast we're going. So if this is our vector field f, it turns into f of x of t. That tells you how the vector field is pointing at time t, like at noon. Where's the vector field pointing? Then our unit tangent vector is the direction we're going, dividing by our speed, so that's a unit tangent vector. So this is t. And then ds is the little distance along the curve that you go in time t. So that's distance is rate times time. So ds is rate, which is x prime of t, times time, which is dt. So if you want to write this out, actually that's how you would compute it. So you have the direction of the vector at any time t, the direction of the unit tangent vector times the amount of time you go with that particular direction. Dot product. This is a dot product. And you can see that these two parts cancel out. You have one on the top and one on the bottom. So we can cancel them. And we can get that this is just the integral from t equals a to t equals b of f of x of t dot x prime of t dt. So if you have just a function and a curve, You can just use this to compute them. You don't have to worry about making a unit tangent vector, because making it a unit tangent vector cancels out with adjusting for the speed. Kind of miraculous, actually, but very nice. So let's try it. So even if you're given some complicated function where you can't just simply say, oh, it's vertical and horizontal, we can still use this formula to compute it. So for example, compute the line integral, the vector line integral of the vector field, which is negative y sine x over x squared, comma cosine x over 2x along the curve consisting of the parabola y equals x squared between x equals pi over 2 and x equals 5 pi over 4. So we have some parabola. I'll draw it over here. Y equals x squared. And pi over 2 is around 1 something, and 5 pi over 4 is something else. Okay, so our curve consists of this part of the parabola. That's what we want to integrate over. Okay, so we compute. Let's see. First, we have to define our curve. So let's say x is t, and then y is x squared. So y is t squared. And since x is t, our t goes from pi over 2 to 5 pi over 4. So that should just trace out exactly this curve that we want. And then what do we need? We'll need x prime of t. So let's compute that. X prime of t is, derivative with respect to t of t is 1. Derivative with respect to t of t squared is 2t. And then we'll also need f of x of t. So f of x of t is f of t comma t squared. And f says, okay, you take negative y, so that's negative t squared, times sine of x, so that's sine of t, and you divide it by x squared, which is t squared, comma cosine of x, so that's cosine of t over 2x, so that's 2t. And now these two t squareds cancel. So this is just negative sine t, comma cos t over 2t. Okay, so there's our function, and it tells you how the vector field is pointing at any time t. So now let's integrate this thing. Okay, so the vector line integral over c of f dot t ds is the integral from the t's that we want. So t equals pi over 2 to t equals 5 pi over 4 of f of x of t. Let's see, f of x of t dot x prime of t dt. So let's put it in. This is from t equals pi over 2 to t equals 5 pi over 4 of f of x of t. That we figured that out. That's negative sine t, comma cos t over 2t dot x prime of t. We figured that out. It's 1 comma 2t. And integrate that dt. And now these are vectors, but we take their dot product. It'll give us a number. So we go from t equals pi over 2 to t equals 5 pi over 4. Okay, negative sine t times 1. That's negative sine t. Plus cos 2t over 2t times 2t. That's cos t. And we integrate that dt. Whew. And now this is something you can do. You can take the antiderivative of both of these things. I guess it's like cos t plus sine t, and plug in from t equals pi over 2 to 5 pi over 4. So the idea of that was that we don't have to worry about making a unit tangent vector or anything like that, because our two speeds cancel out as long as we can parameterize our curve and then we plug the parameterization into our vector field, we can figure out what the contribution is from the two vectors at any point. So this would tell you at any time t, you can figure out whether the vector field is going towards you or against you by just plugging t into this equation. So for instance, if t equals 0, negative sine of 0 is 0, cosine of 0 is 1. Okay, the vector field is helping you at t equals 0. And so on. You can plug it in at pi. I guess pi is on here. Negative sine of pi is 0, cosine of negative 1. So at pi, it's going against you. So this would tell you how much it's hurting you or helping you at any time. And then we just add them up for all of our times. Yeah. Questions or ideas? All right, it's so useful. Now you can go and figure out how hard you're going to have to paddle on your next canoe trip. All right, see you later.